Okay, welcome back to lecture 5. Okay, we're moving on to part 4 of that lecture. We're in the midst of developing some of the formalism of 4 vectors and 4 tensors for use in other applications in relativity. Okay, and I stopped last time after I thought we'd had enough of new formalism. Gave you a break, so we've had a recitation section in between that time and now, and you're feeling more comfortable with 4 vectors and tensors. So we want to develop it a little bit further here, and we want to also look for some new interesting 4 vectors, operator 4 vectors. Okay, they're going to play an essential role, of course, in the development of differential equations for relativity that are going to be essential. They'll be essential in the development of Maxwell's equations. So last time we ended up by noticing that we could define objects called tensors that depended not on just one index, mu, but depended on 2 indices, mu and nu, and they transform just like the outer product of 2 4 vectors. Okay, so this is what defines them, and remember L mu nu is just the matrix of the Lorentz boost. I can write down what those components are, and I have 2 of them here because I have 2 indices. So the upper indices, the contravariant indices, match on both sides. Mu and nu are fixed, mu and nu, and the other indices are summed over. That's to make the matrix product. Okay, sigma and lambda are summed over. Okay, I sometimes refer to that as a contraction of the indices. They're summed over from 0, 1, 2, and 3. It's called a contraction. Okay, and so over here that sum consists actually of 16 components. But of course, it's not really that complicated because most of the members of these matrices are 0. Okay, and so it's not nearly as nasty as that, and it's easy enough in examples just to write it all out, and the formulas for the L's are simple and work things through. Well, examples of tensors, well, it's going to be the simplest one, of course, is the metric itself, G mu nu. Now, later in the course, when we do electricity and magnetism, when we study the electric field and the magnetic field, we'll develop another second-rank tensor called the electromagnetic field strength. It'll be written down as F mu nu. F mu nu will satisfy this transformation law when you transform electric and magnetic fields from one frame to the other. Right, so that's going to be very essential and important to us because we'll want to know how to transform electric and magnetic fields from let's say a center of mass frame to a lab frame in various applications. And there are going to be other examples. When we do general relativity, the important second-rank tensor is going to be the energy momentum tensor of mass energy. Okay. Now in special relativity, G mu nu is especially simple. Okay. And why is that? Well, because the metric, the interval, is invariant under boosts. Okay. So ds squared is the same in the frame S as it is in the frame S prime, as we've discussed several times in the context of Minkowski diagrams, in the context of Lorentz transformations, in the context of energy momentum conservation, etc. So in this particular case, G satisfies this rule from transforming from one frame to the other. I'm just writing this out. Okay, in the case of the metric, I've written it out for covariant indices rather than contravariant indices. Either way will do. Okay, and I've noted here that when you do all the arithmetic, you just reproduce G mu nu. Well, why is that? Well, that's stated right over here. The metric, the interval, is the same in both frames, and I've written it down in Cartesian coordinates. So G prime mu nu, the G here, is just 1, minus 1, minus 1, minus 1, and zeros everywhere else. And that's the same as the G originally, which is 1, minus 1, minus 1, minus 1, zeros everywhere else. Okay. And so I ask you in the problem sets, for example, to confirm that if you plug in the Lorentz transformations for this particular G sigma lambda, that it will reproduce itself. Okay. And just check my arithmetic, but you know it's true from basic principles, and the notation, the mathematics is just reflecting that. A few words about raising and lowering indices with G mu nu. We introduced this idea very briefly last time, but for example, I can this is by definition, I can move from a covariant 4 vector with a lower index to one with an upper index by multiplying through by the metric G mu nu. Well, since G mu nu is either 1 or -1, that's a trivial thing to do in special relativity. But in general relativity, the metric becomes an important dynamical quantity. It'll have off-diagonal elements, and there'll be more to this formula than that. But we'll introduce the formalism now just to get used to it, and to have a nice, handy shorthand for dot products of 4 vectors, as we've already discussed. So we'll raise indices like this, and be very careful with the details here. The G mu nu has upper indices, the A here has lower indices, and the A here has upper indices, and you sum over the second index to contract it. In this case, G mu nu is a symmetric matrix, so you could have written it backwards as well. You lower indices with G mu nu, where G mu nu are lower indices, and I've written that down here. Now I could take this contravariant vector, lower its indices, and I can plug it into this formula and raise its indices, and I got to get back to the same thing I started with. So plug this into this and realize that the inner product, or this product of the two metrics, has got to be the identity. Kronecker symbol is the identity, right? It's 1 when the indices are the same and 0 otherwise. And so that has to be an identity, and we can check that. We can just work through the details and check it out if there's any skepticism there. Okay. Now we know how the 4 vector x mu transforms in the contravariant case, because the contravariant case was the ordinary case of t, x, y, and z. Okay, and we've written that out already. Now the covariant 4 vector differs from the contravariant one by the minus signs as shown here. Okay, and so I can write down the transformation property for the covariant 4 vector just by switching some signs around. Okay, and so here I introduce the notation for transforming the covariant 4 vector with the lower index mu, okay, which corresponds to the lower index mu on the Lorentz transformation matrix, and then the upper indices sigma contracted against the lower index sigma on the covariant 4 vector in the original frame. Okay, okay. So just working that out and watching these signs here, we'll see that the Lorentz matrix with the indices arranged in this way, okay, just has a couple of sign switches compared to the Lorentz transformation in the case of the contravariant 4 vector. Okay, so it looks like just we're juggling some signs around. There's nothing mysterious about it, but it's going to be a payoff later, as I said, to get used to this excessive notation in this case and be able to apply it later. For the purposes here, I can just explicitly write down my Lorentz transformations, okay, and do all the calculations explicitly. It's all very easy, but I'm just introducing this notation for really later use, and just to be able to write some of the formulas down in elegant fashion. Okay, but don't get scared by it, okay, because you can always just go back by writing things down explicitly in terms of t, x, y, and z, and check all this stuff out all this out explicitly. Here I have to be very fussy about putting L, upper mu in the first slot, lower sigma in the second slot. And then if I do the transformation for the covariant 4-vector, I'll write L and then mu in the first slot lower and the second slot upper to have a consistent notation consistent with raising and lowering indices as I've defined it over here. Okay, so check the textbook and the appendices if you feel at all uncomfortable with that notation. I think the only way to do it is to stare at it and to play with it and do some of the problem sets to illustrate the use of the notation. Okay, and now we come to an interesting question. What about other 4 vectors? In particular, we know that when we do physics, we make forces, we take gradients of potentials. Okay, we want to look at time dependencies of quantities, we take d by dt's. So we want to know how operators transform from one frame to the other. In particular, how does d by dx sub mu transform, and how does d by dx upper mu transform? Okay, well, these fellows are going to just differ by signs, plus and minuses in the appropriate places. So it's, if I get one, I get the other, just basically for free. I have to be fussy about my minus signs. Okay, but I can make this. I can see how gradients transform. Okay, because I can go back and write down my Lorentz transformation, and it's convenient for me to write down the Lorentz transformation written for covariant 4 vectors. So I've written it down from the frame S prime to S in the covariant case. So check that my signs, minus signs here are correct. But I'm just writing down the Lorentz transformation that we've already written it down lots of times before, and I'm just writing it down using covariant notation like that, and watching my pluses and minuses. Okay, so the things I'm going to need to see how these gradients transform when I use the chain rule to get their transformation laws is I'm going to need to know how dx depends upon x0 prime and depends upon x1 prime. So I'll need the derivatives, for example, of dx0 by dx0 prime. Well, I read that off here. I see it's just gamma, right? Okay, and then I'll need dx1, for example, dx1 differentiated with respect to d0 prime. Okay, and so I can read that off here. See, here's x1 and x0 prime. Take the derivative. I see it isolates a gamma minus v and a c, so I get that. And then similarly with all the components, I can tell you how these partial derivatives behave. Okay, they just isolate components of the Lorentz transformation. So that's good. That then now allows me to write out the chain rule. I want to imagine doing a derivative of with respect to the time, okay, in the frame S prime, and write that as derivatives of space and time in the frame S. Okay, so I just write down. So now x. So x prime depends upon x1, x2, x3, and x0. So I apply the chain rule to write the derivative with respect to x0 prime in terms of the derivatives in the frame S. And I've just written down the chain rule for that, okay, right there. So remind yourself of that if you're rusty on that. It's in the appendices. Just the chain rule, just changing variables in taking derivatives. Nothing special to relativity here. I'm just doing the basic mathematics of the chain rule so that I can calculate how operators transform from one frame to the other. Okay, so there it is. Okay, and now I know what these coefficients are, the dx mu dx0 prime, because here they are. Here are the non-zero ones. I have two of them. Okay, when I do the chain rule, I have to sum over all the coordinates x mu, okay, because x0 prime can depend upon x0, x1, x2, and x3. Okay, so I have four terms to enumerate. Only two of them are non-zero. Okay, I know the coefficients. I pull them off here. Okay, and I pull this one off here, and I get this as the transformation law. So I see that differentiating with respect to x0 prime is a linear combination of differentiating with respect to x0, that's differentiating with respect to time, and differentiating with respect to x1, that's differentiating in the direction of the beam. Okay, and so that's the case there. And then I need to know how to differentiate in the x1 prime direction. Okay, so I'm in the frame S prime in the x direction, and I want to calculate the derivative in space in that direction in terms of the derivatives in the frame S. That's going to mix in the derivative of time in the frame S and x in the frame S. And I've written that down here by the chain rule, written down the two terms that contribute. I pull off of my exercise here of writing down the Lorentz transformation explicitly and getting the partial derivatives and plugging them in here. You see, I get this one here, which is just gamma. I get this one here, which is minus v over c gamma, and I plug them in. Okay, and now I look at the final result, and I see that it has the same structure as a Lorentz transformation for, in fact, my contravariant position for vector x mu. The minus signs are critical in saying that it's the transformation law for x upper mu, not x lower mu. Okay, so I track that through, and I see that the derivative that I'm calculating, dx sub mu, transforms as the contravariant for vector x mu. So I write that down in this more suggestive form. D by dx sub mu is equal to, I put a differential, and I put it with an upper mu. It's an upper mu because this character over here with the x sub mu in the denominator transforms like x mu with the mu upstairs. So my d upper mu reminds me that the character on the right transforms as a contravariant for vector. And then I know how to write down its transformation law. I just steal it from an earlier lecture where we discussed the transformation law of x and t. I do the same exercise with differentiating with respect to x upper mu. I find in that case that there's a flip. It transforms like the covariant for vector. And I write, so differential sub mu, by definition, is the differentiation with respect to x upper mu. And I write lower mu here because this object transforms as a covariant for vector. The pluses and minus signs show me that that's the case. Okay, so verify that arithmetic. It's very simple. You can do it without using any fancy indices, mu and nu, but at the end of the day, make those identifications so you verify these particular rules with the covariant and contravariant indices, because we'll want to be consistent about it later. I'll show you how keen that is here. So for example, once I have these gradients, okay, and I know that they transform in particular ways, I can make other operators out of them. In particular, I could take the dot product of this one with this one, okay, and I know that if I take the product of them and sum over mu, that I get an invariant operator. So let's do that. It's called box squared, and it's this sum of d mu upper, d mu lower. And we know from our previous examples of what that's going to look like. That'll now be a second derivative with respect to time minus the Laplacian squared. Why the minus? Well, that minus sign, of course, comes from you know, the minuses that appear between the contravariant and the covariant components. Okay? And we might recognize this as the wave operator. Okay? Maybe you've seen that before. We'll find it again when we discuss the Maxwell's equations. Okay? But it's nice to see it here. It's a natural construction coming out of our discussion of covariant operators, and we learn immediately that this object is an invariant object. It's the dot product of a couple of 4 vectors, so it's guaranteed to be an invariant operator. It's the same in any frame. In particular, I write that down here. Box squared. I can do the operation in the frame S. I can do the operation in the frame S prime. Okay. These dot products of the 4 vectors are invariant. Okay, so I'm going to get the same result as here. The wave operator in S is the same as the wave operator in S prime. Okay, that's going to be a very useful operator for us, and we see that it has special meaning in relativity because it's an invariant. It's an invariant operator. Okay. So again, I think that's enough of formalism for the time being. Okay, the last part of lecture 5 will be a discussion of applying the conservation laws of momentum and energy to collisions in elementary particles. These are collisions in which the particle number is not conserved. Okay, in which mass is not conserved, where mass is converted into energy or energy is converted into mass. But we have the conservation laws of relativistic momentum and relativistic energy that guide us. So let's do that next time.